Hello, my name is Mr. Wilke, and we're still under quarantine, which means I can't even get to my classroom to use my smartboard. So we set up a whiteboard in a spare bedroom, and we're hoping for the best. So bear with me, we're working out kinks, but we'll see how things go. All right, so we're going to talk about inference for two-way tables today. So we did chi-square goodness of fit last time, so two-way tables. We remember learning these. This is for categorical variables. Remember, we couldn't find a correlation between categorical variables, but we can find an association, see if they're related, see if they're the same. So inference for two-way tables, when we want to compare several proportions, we put them in a two-way table. All right, so we want to compare several proportions, we put them in a two-way table. We're going to use an example from our textbook. This is an old experiment for quitting smoking, patch and drug, placebo. Now, is it possible to have a placebo for all of these? How clearly, if you're on the patch, you know you're not on the drug, right? Or they give you a real patch and a fake drug. Here, you get a fake patch, real drug. Here, both are real. Here, both are fake. Okay? So nobody should know what they're getting. Should be double blind. All right, so here's how it went. So on the patch, we had 244. The drug, 244 both. 245. Placebo, 160. So let's look at the number of successes. On the patch, 40. On the drug, 74. On the patch and drug, 87. On the placebo, 25. So we do not want to do individual tests. We don't want to say, okay, well, let's test the patch versus the drug. Then let's test the patch versus the patch and drug. Test the patch and that's going to be way too many inference problems. We don't want to do that. We want a single test to see, are they the same? Is there a difference? Can we look at it and see what's the most different? What are we going to do? All right, so we want to do one individual test comparing them, okay? We want an overall test to see if there were differences, and then we'll do a follow-up analysis. All right, so here's our stuff right there. Cool? Cool. Okay, so what we're going to do, we're going to arrange our data in a two-way table with successes and failures. So we've got treatment subject successes, so what do we need to add over here? Let's add our failures. So if there were 244 total, that's our marginal distribution here, 244, 40 successes, how many of them were failures? 204 is correct. Be 170, 245 minus 87 is 158, and that would be 135. Okay, so let's just look at this part. So I'm going to get rid of all of that using the magic of video editing. And look at that. So there's our two-way table. All right, so this. How do we describe this table? Is it a 2x4 or a 4x2? No, it's 4x2. There you go. Good. It's a 4x2. So 4 rows, 2 columns. Good, okay. So each count occupies a cell of the table. All right, so we want to do a hypothesis test. What's our H naught going to be? We want H naught to be no differences, right? So we're going to test H naught, P1 equals P2 equals P3 equals P4, HA. Now, is it going to be is not equal to? Is not equal to is not, no, because some can be equal. HA is going to be, you got it, at least one is different. Good. Okay. So we're going to compare the observed and expected counts, and so compare the observed and the expected counts. Okay? So we'll get to that in just a second. Ready? Erase. Okay, so you'll notice up here, I erased everything. I rewrote the two-way table, patch, drug, placebo, patch, drug, success, failures, totals. Now, I also put in totals at the bottom. So 226 total people quit, 667 failed, 893 total, which means the proportion of people that successfully quit, successful quitters, is 226 out of 893, which is about 25.3%. All right, so 226 out of 893 total quit. Now, how do we find the expected counts? These are the observed counts. We need to find the expected. So the expected counts. Is going to be, for each thing, will be row total times column total over table total. So if I wanted to find the expected counts here, I would take 244 times 226 over 893. Now, remember, 226 times 893, or over 893, is 25.3%. This is the proportion that quit. So this will give me the number who took the patch times 25.3 number who quit. I work this out and I get, what do I get? Well, I guess we should use our calculator. Can you guys see the calculator here? So there's the calculator. We take 0.253 times technology. 0.253 times 244, and that equals 61.732. I don't know how well you can see that with the lighting in here, but there you go. Now, that's the expected. Okay, so how are we going to do this? Clearly, it's going to be some sort of chi-square test, right? We can agree on that. Yes, we knew that. It's the chi-square chapter that we're working on. Clearly, it's going to be a chi-square test. Okay, so let's clear some of this off so we can look at it. And you guys, everybody's got this copied down, so you have it. All right, I'm going to clear this off so we can talk about what we're going to do. I'm going to try to leave this here, or I'll rewrite this so we have it still, and we'll go from there. So much easier in a classroom without this small whiteboard. Okay, we do what we can. Ready? Here we go. All right, so rewrote this, wrote this, so let's talk about what this says. When we do a statistical test, we can find out if the differences in observed and expected counts are significant. We don't compare proportions, we compare observed and expected counts. All right, so we've been talking about chi-square. Does anybody remember how do we calculate the chi-square statistic? So chi-square is the sum of observed minus expected squared over expected. Now the sum will be over all cells in our 4x2 two-way table. Okay, so we're going to figure out each of these. Now, we did this one, it was 61.73, so 61.73 minus 40 squared. We did that wrong. Let's try that again. Observed minus expected, it's going to be 40 minus 61.73 squared over 61.73 plus, and we're going to do this for all of them, but let's make it a little bit easier. We're going to use our matrix and our chi-square test in our calculator. So let's look at the calculator. I don't know how well you can see it. There it is. I feel like the light isn't working. Oh, there. Maybe we can see that. So we're going to go to Stat, go over to Tests, and find our chi-square test. So this says observed, expected. This is our matrix, okay? Now the nice thing is we put our observed matrix in and it'll calculate the expected for us. So let's go to matrix A, hit second, x to the negative 1 is matrix. I'm going to edit. Matrix A we said is a 4 by 2. All right, so 40, 204, 74, 170. All right, does everybody have their calculator? Get your calculator out. If you need to pause this, hit pause, that's okay to do. Get your calculator out, put this observed two-way table into matrix A. So 87, 158, 25, 135. Now, let's go back to our chi-square test. So Stat, go over to Tests, chi-square test, observed in matrix A. This is going to put the expected into matrix B, calculate, and let's see where we're at. chi-square equals 34.937. P-value is 1.256 times 10 to the negative 7th. Degrees of freedom equals 3. So let's talk about how all this works. Now, first, let's look at our matrix. You'll notice this went from a 1 by 1 to a 4 by 2. So if I want to look at matrix B, just do that. 61.75. That's what I had instead of 7.3, right? Good, okay, we remembered that. I'd like to say we could edit that out in post, but you know we're not going to. Okay. So there's matrix B, 61.75, 61.75. I did it twice. Let's do that once. Here we go. Matrix. That's not it. Matrix, there it is. Matrix B. All right, so there's our observed matrix. Can we see it? Good. And if we scroll over, we'll get the other side of the expected matrix. All right, so what does this tell us? Well, p-value there, degrees of freedom there. How do you think I got 3 degrees of freedom when there's 8 different things? So what do you think? Well, if I have this is free to vary, that one's not. Free to vary, not. Free to vary, not. Not free to vary, right? Because these 3 are, oh. So there we go. Degrees of freedom. Number of rows minus 1 times the number of columns minus 1. So we had a 4 by 2. Four minus 1 times 2 minus 1 is 3 times 1, which is 3 degrees of freedom. Okay? So, are we going to reject H naught or fail to reject H naught? Our p-value is low, we reject the H naught is correct. Good. So, we're going to reject H naught. This gives us evidence to show that there's at least one difference in the proportions. Okay? So, let's talk about formal inference. I'm going to erase all this. We'll do formal inference. I'll show you exactly what I expect to see, and that way you get all the points possible. Life is good. Cool? Cool. All right, ready? Magic of editing again. Erase. And look at that. Erased. All right. So let's talk about formal inference. Step 1. What do we want to know? We want to know if there's a difference in proportions of stopped smoking techniques. H naught, there are no differences. HA, there is at least one difference. Step 2. All right, step 2. conditions, always. Step 2 is always conditions. What are the conditions? Was it random? Well, what do you think? Problem didn't necessarily say it was random, but this was a real experiment, I would assume. Let's assume randomization, okay? So we assume the subjects were randomized. All right. We learned last time all expected counts were greater than 1. Now, no more than 20% of the expected counts can be less than 5. All of them were way greater than 5, right? Yeah, so let's just say all expected counts were greater than 1 and 5. Okay? We know that it's no more than 20% can be less than 5, but they're all greater than 5. They're all greater than 1. Say both. That way you show me that you know what the things are. And we go on. We proceed with a chi-square test. Now, last time we did one for goodness fit. This one is called the chi-square test for homogeneity of populations. So what does that mean? What does homogeneity mean? That's right, it means they're the same. So we're testing to see if the populations were the same. Good. All right, let's do step 3. Quick, erase the board. And the board's erased. All right. Editing magic. Again, step 3. Step 3, as always, we've got to show our work. So chi-square equals the sum. Now, what you're going to want to do is you're going to want to take all of them and add them up, except that's a lot. That's 8 things. So we don't do that. We do this. 40 minus 61.75 squared what was the last one? 135 minus, I don't remember what it was. It's on there. I'll figure it out later. Squared over whatever that was equals, and of course, I forgot what everything is. Oh, look, there it is, 119.5 over 119.5. And I need all my stuff, so I'm going to do the chi-square test again real quick. All my matrices are already in there. So, chi-square, show your work, equals 34.937. P-value 1.256 times 10 to the negative 7th, roughly 0, right? Okay, low p-value. Also, always in step 3, degrees of freedom. Step 4, interpret in the context of the problem by linking to the p-value. Since our p-value is low, we reject. Since our p-value is low, reject H naught in favor of HA. There is strong evidence to show a difference in stop smoking techniques. Now, you may want to say, what does it look like it's best? It looks like the patch and drug did the best. It looked like the patch wasn't much different than the placebo. Patch and drug was a little bit better than just the drug, but that could just be due to chance. We don't know. So we want to just say this. We do further analysis and see which makes the most difference. And that's it. All right. Does anybody have any questions? If you have any questions for me, you can put them in the Canvas discussion if you're taking the class now. If you're just happening across this, post them in the comments. There you go. All right, well, thank you guys for coming. And yeah, next time we'll learn chi-square for association independence. And then that'll be it for this chapter. Goes quick. All right, have a fun quarantine. I'll see you guys later.